Hi, welcome once again to our workshop called Math as a Second Language. I think I mentioned last time that I was going to introduce a topic that I like to call unadding, but which is usually taught as subtraction. And what it's based on, well, let me put it this way. It's based on the same reason why I chose the theme Math as a Second Language. As we go through this course, what you're going to find is that our adjective-noun theme unifies all of the numbers that we use in arithmetic. In other words, using the adjective-noun theme, we can take any fraction problem and convert it into an equivalent whole number problem. In other words, and I'm going to write this down because I think it's important for you to really see it, it's that 100 applications of one concept is much more effective than 100 different concepts, each with one application. One concept with 100 applications is better than 100 concepts, each with one application. Okay, now let's suppose you're a young student and you've only learned addition so far. You've never even heard of the word subtraction. Okay? Look at these two fill-in-the-blank problems. 3 plus blank equals 5, and 5 minus 3 equals blank. Can we say at the very outset that this guy over here is a huge mystery? Because you've never seen this symbol before. You're learning addition now. On the other hand, when you see this, are there any symbols here other than the blank that you're not used to seeing? You've learned the number 3, you've learned the number 5, you've learned what the plus sign means, you've learned what the equal sign means, and you say, oh, this is just arithmetic, but this time instead of telling me both numbers I'm adding, they're telling me one of the numbers plus the answer I'm supposed to get. Now let me think about when I learned my addition facts. I started with 3, what did I have to add on to get 5? Oh, I had to add on 2. Nothing new here, per se. And in fact, in a very disguised form, this is the student's introduction to algebra. All we do in algebra is we replace the blank by an x, or whatever number, and we say for what value of x would it be true that 3 plus x equals 5? Or sometimes we just say, find x, and the kid says, oh, I found it, it's right here. No, again, it's the language with which we say things. You don't say find x. You say for what value of x will this be a true statement? For what value of the blank will this be a true statement? See, in other words, I coined the word unadding in the same way that if you want to say something is the opposite of familiar, you say it's unfamiliar. If you want to say it's the opposite of even, you might say uneven. And based on that, if you asked a little kid, what's the opposite of tall, he would say untall. I mean, notice that the word short in no way resembles the opposite of what tall means. If you're learning English as a second language, you still understand the concept of shorter and taller. But you may know the word tall, but you may not have yet learned the word short. So in a certain sense, I prefer to call, well, like I said before, you say even versus uneven. You could have tall versus untall. And by the way, if you did that, the number of adjectives we'd have to learn would be cut in half, though we'd probably waste time wondering whether we should start with short and have unshort the opposite, or whether we should start with tall and have untall the opposite. We'll always find something to argue about. But the point is, if we say to the student, oh, when you start with both numbers and want to find the sum, we call that adding. But if you start with one of the numbers and the answer, we call that unadding. But when they ask you test questions, they're going to call that subtraction. In other words, I'm not saying that the student shouldn't learn the proper vocabulary. I'm saying it's very nice if they can internalize the concept before they see the formal definition. Now, there may be times when the formal definition is easier to introduce than the concept. I just haven't found any in the way I enjoy teaching. I've always found that if you can lead people into the concept by conversation, it becomes much more natural for them to internalize what the important point is. Really important point. Please avoid having the students read 5 minus 3 as 5 take away 3. Now, You say, but it's easy. Look, all you have to do is start with 5, and you take away the 3, and what's left is what you have to add on. It's very simple. If I have 5 and I take away 3, I have 2 left. I would prefer that the youngster read this as the 3 I already have, the 3 that are crossed out, plus the 2 that I haven't crossed out, adds up to 5. And the reason I say that, and by the way, you can also do it this way. See, if you want to do it by tally marks, I want to wind up with 5. I already have 3. What do I need to make the 2 batches of tally marks equal? I need 2 more. But here's the problem. Later on, not now, later on the student is going to encounter negative numbers. And they're going to see problems like 5 minus negative 3. How can you take away negative 3 from 5? If there are 5 pieces of candy on the table, the least you can take away is none. How can you take away less than 0? However, there are cases where one can interpret this to have a real physical meaning. For example, in terms of profit and loss, you can think of negative 3 as meaning a $3 loss, and 5 as being a $5 profit. So you can read this. And the question is, what do you have to add on to a $3 loss to get a $5 profit? Well, it's not very difficult to see, well, if I have a $3 loss, I first have to make a $3 profit to break even, and then a $5 profit on top of that to make a $5 profit. So altogether, I have to make an $8 profit. In other words, this has sense, makes sense in terms of what do I have to add to this number to get to this number. But it makes sense even when this is a negative number. But takeaway doesn't make sense when this is a negative number. And this is what's going to happen eventually. Kids are going to stumble, well, how can I take away less than nothing? In fact, historically, the ancient Greeks never talked about negative numbers. They called them imaginary. And the reason was the ancient Greeks visualized numbers as lengths. And how could you have a length that was so short that if it was 2 inches longer, it would still be invisible? See, the concept of negative numbers are not that natural. In fact, in real life, until we get to algebra, we never really have to use negative numbers. If we're dealing with business, we talk about profit and loss, not positive and negative. If we're dealing with temperature change, we talk about increasing temperature versus decreasing temperature. If we're talking with motion, about motion, we talk about motion to the left versus motion to the right. We don't need the words negative and positive when the noun phrases are there. But it's important. This is why in teaching you have to know more than where you are teaching. In other words, it would be kind of appalling if your child's second grade teacher was reading at third grade level. It's equally appalling, even though it happens, if the child's second grade teacher may understand mathematics at third grade level. You have to be able to look ahead. I've had teachers say to me, why am I learning this? I'm only teaching second grade. No, in the second grade, you can begin paving the way for what students are going to see later so they get a smooth transition rather than thinking of something as being a brand new topic. So again, by having students read 5 minus 3 as the number you have to add to 3 to get 5, you're helping them for when they get to an obstacle further down the road. And the important thing is, don't underestimate reading comprehension. As important as mathematics is, reading comprehension is even more important. Here's an example. Don't confuse 3 plus 5 equals blank with 3 plus blank equals 5. You say, well, they obviously look different. Be careful. I have seen students learn to do problems by looking for key words. When they see the word add, they see the word sum, S-U-M, they know it's an addition problem. So when you say to a student, what must you add to 3 to obtain 5 as the sum, it's amazing how many of them will say 8. Because the only 2 numbers they see are 3 and 5, and the only 2 clues they have are add and sum. So if you add 3 and 5, the sum will be 8. No, the problem says, what must you add to 3, not to add 3 and 5. What must you add to 3 to obtain 5 as the sum? This is the danger of teaching students to look for key words, because you can get trapped by having what we call paraphrasing. Somebody uses a different way that doesn't use the key words that you want the student to use. Again, just something that I'm trying to maybe overemphasize to show you the importance of what you can do now to help the student later. I remember there used to be a commercial for a car air filter. I won't mention the name of the company because then I'll have to give them a residual or something, but it was basically they showed you this filter and they showed you what happens when a motor gets clogged. And they said, you can either pay me now, pointing to the filter, or pay me later when he shows you he's installing a new engine block. You see, the student can learn this now and be prepared for when it comes up later, than to have to wait until it comes up later and then he has to use it immediately when he hasn't even internalized it yet. And by the way, we've done unadding a lot. I don't know if you've ever thought about it consciously. When I went to school, we were taught in a problem like this that the way you checked it was you took the answer you got and you added it to the middle number here, and it was supposed to equal the top number. Well, what were you doing when you checked this? You were saying, is this the number which when I add to 3, I get 5? And we do this in change making all the time before they had computers. If you pay for a $2.58 purchase with a $5 bill, the man didn't subtract. He says $2.58, then he gives you 2 cents and says that makes $2.60. Then he might give you a dime, 10 more cents, makes $2.70. Then he gives you a nickel, makes $2.75. Then he gives you a quarter, that makes $3. And then he gives you 2 $1 bills to make 5. In other words, what did he do? He added on to $2.58 the amount necessary to equal $5. If you add up the 2 cents, the 10 cents, the 5 cents, the 25 cents, and the $2, you should get $2.42, I guess. Okay? So we've been doing that. And again, when we do this by what we call unadding, when we want to see what do we have to add on to 123 to get 588, we just do what we did before. Only now instead of the adding these, we say, well, what do you have to add to 3 ones to get 8 ones? Well, the answer is 5 ones. What do you have to add to 2 tens to get 8 tens? Answer is 6 tens. What do you have to add to 100 to get 500? Answer is 400. And again, notice how we were able to rearrange things the way we wanted. In other words, we were able to look at the ones column separately, the tens column separately, the hundreds column separately. The problem that we run into is that students often get confused when you have to have the sum come out to be a number that ends in a bunch of zeros. In other words, how can you add something on to 8 to get 0? 8 is already bigger than 0. Well, what you can say is, what do I have to add on to 8 to get a number that ends in 0? In other words, you may remember doing this. We used to call it borrowing. I can't borrow from here because there are none there, so I'll borrow one guy from here. That leaves me with 4, but now I have 10 of these guys. See, I traded in 100 for 10 tens. Now I can take one of the 10 tens and trade it in for 10 ones, and now I can do the problem. Okay. Well, some people see this, some people don't. They get all confused. Why do we do this? And again, when you put money in, watch what happens. Suppose I have $500. Okay, I can say, okay, I'm going to take one of my hundreds and trade it in for 10 tens. And now if I want to, I can take one of my tens and trade that in for 10 ones. Okay? And now what do I have left here? In other words, another way of saying 500 is 400s plus 9 tens plus 10 ones. It adds up that way, right? 400, 90, and 10 is another 100. Now, when I want to take away the 258, it's kind of easy. I can take 8. What do I have to add on to 8 to get 10? 2. What do I have to add on to 5 tens to get 9 tens? I have to add on 4 tens. What do I have to add on to 2 hundreds to get 4 hundreds? I have to add on 2 hundreds. There's the answer. Again, putting this step in takes a little bit longer. But later, can you see how easy it is to say, hey, I can save space just by crossing out here and doing little things like that? Even so, there are students who have trouble with all these zeros here. Let me show you another technique that was similar to the same sum technique that we used before. The problem we're working on is 500 minus 258. So let's make a word problem out of that. Let's pretend we have 2 historical artifacts, one of which is 500 years old, and the other of which is 258 years old. What's the age difference? See, the gap between their ages is what you get when you, as we say, subtract 258 from 500. In other words, when you add on to 258 the amount that it takes to make 500, you're finding the gap between these two numbers, the age difference. Now, the nice thing about age difference is it doesn't depend on what year you're looking at. If I'm 5 years older than my wife this year, I'm going to be 5 years older than my wife 10 years from now. I was 5 years older than her 11 years ago. The age difference doesn't change. You say, great, I just thought of something. This is a hard problem for me to do. But a year ago, the artifact that was 500 years old was only 499 years old. And the artifact that was 258 years old is only 257 years old. So the gap between their ages hasn't changed. In other words, instead of subtracting 258 from 500, I will subtract 257 from 499. And look how easy that is because of the 9s up here. Okay? So again, I hope this gives you a new insight as to what subtraction is and how it's really nothing more than unadding, a different form of addition. And let me just give you one more problem to just stick for yourself. Let's just see if you get the idea. How do we do this problem? 100,000 minus 48,347. Use the same difference again. Think of these as being ages. A year ago, this guy was 99,990 years old. This guy was 48,346 years old. And now, to solve this problem, all I have to do is solve this problem. Okay? So that brings us to our practice problem of the day. And remember what that is. I'm going to give you a problem. I want you to look at it. And after you've looked at it, in other words, pause the video, look at it. After you've looked at it, return and watch how I've decided to solve the problem. But let me show you what the problem was, because I found students doing this and other students getting perplexed when it happened. In doing the subtraction problem, 582 minus 143, some people were taught to add 1 to the 4 rather than to subtract 1 from the 8. That is, they would take 582 minus 143, and instead of crossing out the 8 and making it a 7, they crossed out the 4 and made it a 5. And the question was, why does this method work? In other words, you get the same answer both ways. But why is this way equivalent to what you would have got if you had crossed off the 8, made it a 7, and did the problem the traditional way? Okay? So come back and watch what I'm doing after you've had a chance to look at the problem. So the problem was 582 minus 143. And the traditional way, meaning the way I was taught, is I would borrow. I don't know why they call it borrow, because I never paid it back. But I guess I did. You see, you said, we'll cross out the 8 and make it a 7, and we'll put the 1 in front of the 2 over here. See, what you really did here was you took away 10 from here and repaid it by making this number 10 more. So that was the same sum problem. you took 10 away from one, gave it to the other. So in doing this problem this way, you were getting the correct answer. Now, the other way is a little bit more subtle, and what it's based on is, this was based on the same sum, this is based on the same difference. Meaning, when I put the 1 over here, that made this number 10 greater. When I crossed out the 4 and made it a 5, that made this number 10 greater. But I'm subtracting, I'm finding the gap between them. If we increase both numbers by the same amount, the gap doesn't change. So in other words, subtracting 143 from 582 is the same as subtracting 153 from 500, 8 tens, and 12 ones. But again, the beauty of the system is that if you understand what's happening, then you're not perplexed if somebody else does it a different way. I remember during the new math, parents complaining to me, they said, this new math is ridiculous because my kids come home and I can't help them because I don't understand what they're doing. And what the parent is really saying is, I never understood it the way I learned it, but I did memorize it. And now my kid is coming home and he's memorized something completely different and I don't know what it means. You see, if you have internalized something, you'll be able to understand and say, oh, all they're doing is such and such a thing. I remember my grandson having trouble with long division because he had just memorized the algorithm. And when I showed him, which we'll be doing in a couple of more lectures, the logic behind the long division algorithm, he said, this is easy. See, I've had students at the community college say to me, why wasn't I taught this way previously? By the way, they might have been, and they've forgotten, and it's very easy to have a false memory and say they never taught it to me this way. But many times what's happened is youngsters have been taught an algorithm in one specific way, and they've memorized it. They have no idea why it works, but they know it does work. And that's what causes the problem. Anyway, I think we've gone long enough for today, and I will meet you all again next time when we will introduce the concept of multiplication, which is also a form of addition, and we'll talk more about that. Until then, enjoy, work hard, and I'll see you then.